Continue the section 13.6, directional derivatives and gradient. Okay, we now define the directional derivatives and we'll introduce the gradient vectors and the meaning of those. Okay, directional derivatives is defined in the following. When u be a unit vector, the directional derivative of f at the point AB in the direction of u is defined as this. When the limit exists, the limit h, when the limit h goes to 0 and f of this over the h, like this. So, if u is a unit vector 1, 0, then du AB is just fx of AB. It's a partial derivative of f with respect to x. And if the unit vector v is 0, 1, then dv AB is a partial derivative of f with respect to y. Okay, so the first example is find the directional derivatives of this function at this point 1 and minus 1 in the direction of 1, 0. Then actually this is just partial derivative of f with respect to x and plug in these values, which can be found in this. And the second and third examples are same. For example, if we have a function like this, then if we give a point at 1 and 2, and the unit vector is a cosine pi over 6 and sine pi over 6, then what is the partial derivative, the directional derivative of that function at this point, at this direction? This is it. For the third problem, for the third problem, if we have this function 4x squared plus 3y squared minus 5xy, then gradient of that function can be obtained in this way. And for this function, the gradient can be obtained in this way. And so now we're going to start. We continue to explain a little more of the directional derivatives. When we find the rate of change of this three-variable function at point P naught, P0, in the direction of the arbitrary unit vector u, then this then we use when we find this one, then we use the directional derivatives. This is why we need the directional derivatives when we find the rate of change of this function at a certain point in certain directions. When we find the directional derivatives, we consider this three-variable function as a function of single variable t when these conditions are given. Okay, and the directional derivative can be obtained in this way, like this. When u is a unit vector, any unit vector, then this can be written in this way. So this can be obtained as an inner product of this vector and this unit vector. So yeah, so directional derivative can be found as an inner product of these two vectors. This gives us a motivation for the gradient vector. Okay, the reason that this equality holds is from the definition. Yeah, we can write the directional derivative in this way, and this can be expanded in this way, and it can be rewritten as a separated two limit like this. And as you see, this part, the first part can be written as a partial derivative of x times this, and u1, and this the second part can be written as a partial derivative of f with respect to x, y at the point x naught, y naught times the unit vector u2. So this can be written as an inner product of these two vectors. One unit vector and one is the directional, the gradient of the function, of the given function. Okay, and this graph shows what the directional derivative means when the unit vector is given, and that the derivative at this point on that direction, this u direction, and this is the derivative, directional derivative on this direction of this surface at this point. Okay. So this example asked us to find the directional derivative of the function f of x, y at the point 1 and 2, and the direction as a unit vector given by angle theta is equal to pi over 6. So we can write the unit vector as a xy coordinate vector like this, cosine pi over 6 and sine pi over 6, which is this. And the partial derivative of f with respect to x at point 1, 2 is minus 3, and fy 1, 2 is 13. So the directional derivative of the function f at this point, at this u direction, is inner product of this vector times this. So minus 3 times the square root of 2 plus 1/2 times 13. So 13 over 2 minus this value gives us the answer that we are looking for. This is the directional derivatives at this point, at this direction. Okay, this can be obtained by this code, and these two are same. Okay, let's see. Okay, this notation, and the gradient vector we're going to define. The gradient vector of this function of two variables can be obtained in this way, and this notation delta f is called the gradient vector of f. Okay. So, this directional derivative is the inner product of the gradient vector of f and the unit vector u, like this. So, find the gradient of f. Then, we can easily define a function x, the variable xy and f of xy as this function, and find the gradient. Then, this is a partial derivative of f with respect to x, and this is a partial derivative of f with respect to y. So it's a vector. And for second, define the new function here, and use the same command to find the directional derivatives, as you see. And this function, then directional derivative is obtained like this, as you see. And for this function, for the second part, directional derivative is obtained in this way, which is exactly the same as what you see here. Okay, interpretations of gradient here. The gradient is not limited to calculating partial derivatives. It plays important roles in multivariable calculus. Okay, it is a very important concept which will be used more and more later. Okay, and directional derivative of f at point AB in the direction of u can be written in this way. But this u, this value, this inner product can be obtained in this way by the rule that you have found from the Cauchy-Schwarz inequalities part. And since this is a unit vector, so this can be written in this way. What this means is, if this is 0, then which means these two vectors are orthogonal, and that means the directional derivative is equal to 0. So when the directional derivative is 0, then this means these two vectors are orthogonal. So these are the conclusion that we can draw from the observation on these relationships. The first one is the gradient f of AB points in the direction of the gradient of the function at the point AB in the direction Okay, here this observation shows the meaning of the gradient at a given point when it means when it shows the direction of the steepest ascent and when it shows the direction of the steepest ascent. And also, when the directional derivative is equal to 0, that means the direction, the gradient and the unit vectors are orthogonal because of this relationship. If this is equal to 0, then inner product is equal to 0, and theta is equal to pi over 2, which means they are orthogonal vectors. Okay, that's the observation. And with those, the definition and observation, we can deal with the examples. Find the derivatives of this function at this point in the direction of the unit vector like this. Then we first find the partial derivative x at the point 3, 4, and partial derivative of f with respect to y at the point 3, 4, and then find the inner product of this gradient and the given unit vector like this. Then what is the direction in which the function f increases most rapidly at p not in the xy plane region? So we found the direction first. First, we have the length of the gradient of f, which can be obtained as a square root of minus 6 square plus minus 8 square, which is square root of 100, and then divide the gradient with the length of that gradient, which gives us the unit vector like this. So this is the direction that has the steepest the ascent. And determine the direction of 0 changes in f at the point 3, 4, which means when we have the directional derivative is equal to 0. Okay, so we solve. So that can be obtained when we multiply this normal vector with this gradient. The gradient is minus 6 and minus 8. So in order to make it the inner product 0, the normal vector should be the same value, the opposite directions, which can be obtained by this it should be a unit vector, so we should use the unit vector which we found here, and it should be a normal vector. So we find different sign of the different sign, which is 4 over 5, and the same sign of the same value at minus 3 over 5 on the opposite directions. So we can, when we multiply, when we find the inner product, that it can be demolished. So from the inner so we, after we find the directional derivatives and we find the normal vector that makes inner product equal 0, and then normalize the length, then that will be the one that we are looking for. Next, gradient and level curves. Gradient and level curves. And recall that the curve f of xy is equal to g naught is a level curve on which function value is constant. Okay. Combining this observation, we conclude that gradient is orthogonal to the line tangent to the level curves through the point AB. Okay, this gives the following theorem. Given a function f differentiable at AB, the line tangent to the level curves of f at AB is orthogonal to the gradient, like this. Okay, the immediate consequence of the theorem 4 is an alternative equation of the tangent line. The curve described by this can be viewed in this. The sage turfers like this. As you see, the level, these are the level curves, and these are the directional derivatives. As you see, at every point, it is orthogonal, isn't it? one is outside, is ascent, one is descent. Those the directional derivatives and level surface together, which clearly indicate the direction. These level curves and directional derivatives are orthogonal at every point of the level curve. Okay? And so we now extend our observation to three variable functions. Okay, suppose you have three variable functions, then directional derivatives can be obtained in this way, and which is the and the gradient can be obtained as a three-dimensional vector like this, and we can deal with the problems involving the three variable functions like this. Find the directional derivative of a function of three variables like this at this point, at this direction. How? So, in this case, we find the partial derivative of f with respect to x, y, and z at the point 1, 1, 0. Right? So we have a vector of 2, minus 1, and minus 1. 2, minus 2, and minus 1. And we draw the unit vector from A by normalizing the vector. Just divide by the length of that vector and norm of the vector. And then find the inner product of these two vectors, this one and that one, which gives us 4/7. Okay? And estimate how much the value of this function will change if the point P moves delta S is equal to 0, 1 unit from this point to this point. Okay, here, what we need is the unit vector of the direction from P0 to P1. So we subtract P1 to P1 to get a direction vector, and then normalize it to have the unit vector U like this. And we find the directional derivative of f at point 2, 0, 0, which is 1, 2. So we find the directional derivative of f at the point P0 as inner product of this vector and this unit vector, which is 4/3. Then delta f is approximated by the directional derivative of f at that point times the change of s, which is 0.1 unit, which gives us 0.13 unit as the changes of f when this point P moves delta s unit from this point to this point. So that is the answer. Okay, then plot the contour plot and level surface of this function. And this can be obtained, can be done in here, gradient 3 point, and this can be shown as the directional derivatives and gradients and plot and plotting these functions and 3D plotting of all these shows many different functions only. And this is the general form, and this is explanation of directional derivatives with this is code that you can simulate as if you change the point as different one, then it gives us the directional derivatives and contours and things. This is a visualization of directional derivatives. And so just to practice it, and you just change the function to draw the contour plot and level surfaces. I think that's the end of the section 30.6. The next section is the tangent plane. Any questions?